Hello everyone. We are looking at this midterm problem from last year, midterm 2019 fall. So let's see what we have here. We have a set of natural numbers between 1 and 10. That seems easy. Builder notation, that's easy. We have subsets of size 3. Okay, that's things like some 3 things, right? And then the restriction, only even numbers. And then part number 3, we have the same like in here, but with another restriction, additional restriction. And we have a combinatorial problem here with a sequence that has to be in order with elements from this set. So let's take it little by little. Let's see how far we can get here. So first of all, I would if I've been in an exam, I was in many exams. If I've been in an exam, I would just for a simple problem like this, I would just write down the set to have it in front of me. Right? It's not possible in every single problem because some sets are really big, really long, but this one it's easy. It's 1 to 10 natural numbers. So let's do part 1, set builder notation. That's a simple problem. So these are obviously natural numbers, and it's between 1 and 10, right? So that is that. Okay. Now part number 2 here, we want how many subsets of size 3. Well, if it only be this subsets of size 3, so I'm going to do here part 2. If it only be this subsets of size 3 out of say k elements set, that would be k choose 3. But the problem is in here in part 2 we have a restriction, so we only have even numbers. So our set, this k element set, that is not whole A. So then let's cut the subset that we care about. So let's say B is the even elements of A set. So kind of like B is only the even one, 2, 4, 6, 8, 10. So then the size of B, that is this K, is 5. So then the answer is 5 choose 3. Again, the trick in here is not to consider the whole A, because we only want subsets made with even elements. So we take the even elements, we put them in a set B here, and then we make the subsets out of that. So part 3, we can do part 3 in more than one way. We can say, okay, well, in part 3, I think a reasonable approach would be to say, okay, it's all subsets in part 2, the one we just counted. That will be these ones right here, except the ones that fail the restriction. So what is the restriction? The restriction is contain, that's part 2, contain not 2 and 4 both. So we have 5 choose 3, 5 choose 3, that's again, that's from here, from part 2, minus the number of subsets that contain both. That is the negation of this restriction, right? Not 2 and for both. Now we say we want to count those invalid ones. That's the one that contains both 2 and 4. 2 and 4. So now we're looking at this, what those subsets look like. Well, that will look like they have to have 2 and 4, and they have to have some other x, right? Because the size is 3. We only looking at 3 size 3 subsets here. So this x could be the additional element. There has to be not 2 and 4, right? They have to be 6 or 8 or 10. That will be the other 3 elements here in B that are not 2 and 4. So I think there are 3 such subsets, right? This number is 3. 3 such subsets. Because I can plug, instead of x, I can plug the 6, the 8, or the 10. So then the answer is 5 choose 3 minus 3. Now we can do this in another way. So 3 again, solution number 2, if you like. Solution 2 for still 3. I can look at B, which is I have it here. This is B. So I can break these 2 and 4 apart. I can say that's 2 and 4 union partition, like the other part, with 6, 8, and 10. And then again, what 3 is asking is we want the subsets of size 3, excluding the ones with both 2 and 4. So now I'm looking at my partition here, and I'm trying to build these subsets. Let's say want. That's what we want. So how can I build those subsets? I'm gonna break this B into kind of like B1 that contains these 2, and this B2 that contains those 3. So B1 is 2 and 4. B2 is 6, 8, and 10. And I'm thinking, what are the options here for such subsets, right? I can have one element from B1. I can have both 2 and 4, but I can have one of them, right? 2 or 4. And 2 elements from B2. Remember, I need a total of 3. So that would be, I pick 1 from B1, that's 2 choose 1, and I pick 2 from B2, that is 3 choose 2. Or I could have no element from B1, just choose all 3 from B2. That would be 3 choose 3, that's one subset. That has to be the whole B2. So the total, if I am to sum up, I think that disjoint, these are disjoint cases. So total, it's a sum rule. It's 2 times 3, that's the first case, plus 1 in the second case, that's 7. I think we should verify the 2 solutions. This is solution 1 right here. So let's sanity check. In solution 1, we have 5 choose 3 minus 3, 5 choose 3 is 5 factorial, 3 factorial, 2 factorial, minus 3. That is 4 times 5 by 2 minus 3. That's 20. 10. 10 by 10 minus 3 is 7. Okay, so it checks out. So it means we have both solutions producing the same answer. That's a very good thing, right? So let's look a little bit into part 4. This one. For simplicity, I rewrote 4 in here, so we can look at it again. What we have is the original set. Remember, so we had A. That is our set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we want to create a sequence like this one here of 15. So we have 15 elements. That's fixed. We have a fixed order. The sequence has to be increasing. So we can have the 3 you know, after the 5. We have to have them. You see how we have the 1s, and then we have the 2s, and then we have a 3, and then we have the 5s, and then the 6, and the 7, 8, 10. In fact, that's the hint. The hint is saying that these sequences are purely determined by how many 1, 2, 3s, 5s, and so on and so forth you have, right? So the way to see this sequence, I think, in a better way, would be to take this sequence and to say that's really not like a sequence. I want to write it like in chunks. So I'm going to say the chunks with 1, I have 1 2 times. Let me write it separately so we can see. 2 times. And then I have 2 3 times, right? Because there are 2 is repeated 3 times. Then I have 3 that is only 1 time. You see the 3 right here. Then I have 4. I'm gonna include 4. 4 is 0 times, right? Because there is no 4. No 4. And then I have 5. That's a big chunk of 5s right here. So that is 5 of them. And then I have 6. That is 1 time. Then I have 7. That is 1 time. Then I have 8. 1 time. And then I'm going to include a 9. That's 0 times, because there's no 9, right? So we have 6, 7, 8. There is no 9 in there. And then I have the 10, which is 1 time. So now, did I do this right? 2, 3, 1, right? That's 6. So the total of these counts, total count, must be 15, right? So we should verify that again. 2 plus 3 plus 1, that is 6, plus 5, that's 11, plus 1, 1, 1, 1, that's 4, that is 15. Good. So that's good. And then we have here no 9. So I really think we should see it this way. We have the sequence. It's effectively chunks of each digit or each number here that is valid. That's in A. It's repeated a bunch of times. So I really want to think of those like bins. I think, right? This is bin 1. That's bin 2. That is bin 3, bin 4, all the way to bin 10, right? And then I'm throwing items. I have 15 items. That would be my balls. because the sequence has to have 15 numbers. So the items are those sequence values, which I don't know what values I'm going to use. That's why I throw the values into the bins to see what values come out. Into 10 bins, those are the valid options, valid elements from A. So of course we know how to compute that number, the possibilities of 15 balls into 10 bins. It's a formula. But before I apply it, so we can compute that formula below here. It's 15, right, plus number of beans, so it's balls plus beans minus 1. So beans is 10. Choose beans minus 1, right? So that's the formula. But more importantly, we want to make sure we're counting this correctly. So we want to make sure we have two things. Every sequence can be obtained, every valid sequence can be obtained by balls into beans. So that's effectively what we've already done. We were taking a sequence, so we take any valid sequence, and of course this sequence breaks up into those chunks, and because we have arranged it into chunks, it means it can be generated by the balls into beans process. If we throw the balls, however balls go into bin 1, that will be how many ones we have in the sequence, and however balls get into bin 5, for example, that will be how many 5s there will be in this sequence. So it will be 5 in the example. But then you also have to check that the balls into beans procedure only produces valid sequences. For our count to be right, we have to ask ourselves, is there any arrangement balls into beans that is not a valid sequence? Sometimes there are limitations in problems, and sometimes we have to take out some of these balls into beans arrangement because not all of them produce the correct sequence. But in here, if we are to imagine those balls, those beans, right? We have 10 beans, 1, 2, 10. Any particular throw of balls, you know, if I have say 6 balls in here and 9 balls in here, that could happen, right? So this is, say, for example, bin 3 and bin 4. Would that correspond to a sequence? Of course, that will be 3, 3, 3, 3, 3, 3, right? Because there are 6 3s, followed by 9 4s. What if all the balls fall in one bin, only one bin? That also works because I'm going to have 15 of that bin, right? And then the last thing we want to check is any double counting. That is, there are 2 balls into beans arrangements that actually are the same sequence. So of course we have to avoid that, or if it's not avoidable, then we have to subtract that number. But in here we check this and we check this and we check this, and then it's a one-to-one map between balls into beans and the sequences. So the answer will be this combinatorial value.